Welcome. This is the second to last lecture we will have on topics related to SCP-140, which is topics in astronomy. So far, we have looked at astronomy from a lot of different perspectives. We started off by looking at what we could just observe and learn about from experiments here on Earth and telescopes and observations. And we've since then moved out beyond our planet into the solar system, exploring the stars. And now we're going to think about the building blocks of, as far as we can tell, all of reality, what we now term the universe, the limits to everything that we can observe and know that exists. For a long time, we didn't know what made the universe up. 400 years ago, the idea was that the Earth was the center of all of reality and everything spun around it. And that was turned on its head by certain observers, astronomers, philosophers, and scientists who saw that some of the observations that we made from here on Earth didn't make a lot of sense unless you consider the sun to be at the center of all things. And then even more interesting than that, as we began to explore and explain how this might be, we began to realize that the sun was just one of many of millions, actually billions of stars that were more or less the same. Some were bigger, some were smaller, but none were the center per se. People began to ask the question, well, what is the center of all these things? And there were some debates about this about 120 years ago. Since that time, we've come to understand that stars tend to group up in really gigantic structures we call galaxies. The first galaxy, as it were, was our own. We call it the Milky Way, which is where the word galaxy comes from. The Milky Way is a road of sort of milky light that you can see from dark sites here on Earth. And that's actually indicating where the distribution of most of the stars near us lie. It's in some sort of band across the sky. And as people began to investigate this, they began to realize that there were other systems very similar to this, but much, much further away. And each one of these individual systems are what we now call galaxies. Galaxies are the building blocks of our universe. And we're going to explore different galaxies by looking at the images that we can create of them using really advanced telescopes, materials that really weren't available until about 100 years ago to measure what these very, very distant objects are like, what their features are, and how they're distributed throughout all of reality, what we call the universe. Our next topic will be cosmology, which is thinking about the universe as a whole. What are the different features that the universe has? But for now, we're going to focus on galaxies, starting with our own and then moving out to the furthest reaches of space. So we start off from chapter 25 with the first figure, where we can see our own galaxy, the Milky Way. This is a view from Utah, and we're looking at the center of our galaxy in the constellation Sagittarius. Now, if you could see the entire view of our Milky Way, it would be pretty obvious that this was the center. And then on the opposite side of the celestial sphere was the direction out of our galaxy. We're about 2/3 of the way out this collection of stars. But there's also a lot of weird things going on. There's sort of a dark band that runs across the galaxy, and this is something that is a feature of our galaxy. We've got a lot of dust that obscures many of the stars that are further away. And that's happening in this image here. If we had infrared eyes that could see through that dust, we would see that the vast majority of stars are in the direction we're looking at right now. But it's a little bit unclear to tell that that's what's going on just from this view. People began to map these distributions of stars some 300 years ago, 200 years ago. They really got together and set up these maps. And this was one of the more famous ones made by an astronomer named Herschel. What Herschel noticed was that the sun wasn't at the center of this distribution of stars, but that they sort of was bizarrely asymmetric and also like a band. This was done more or less to by counting stars in various directions and making a judgment call about that most stars were roughly the same luminosity. Now, we know that's not exactly true, but this was a pretty good first attempt. It was about 100 years later when Harlow Shapley, another famous astronomer, thought that a better way of trying to figure out what the grand structure of things were would be to look at clusters of stars rather than individual stars. And the clusters of stars he chose were things called globular clusters. And when he found the distance to these globular clusters using a very clever method where he was able to figure out what the brightest stars in those clusters were by looking at the age of those clusters, and that gave him a way of figuring out the distance, he could then kind of make this map all the way around reality. And this is the one he came up with. So you can see what Herschel had done before him and what Harlow Shapley did after. He decided that the distribution of things was a little bit different than what Herschel thought, kind of more like a ball surrounding the sun. We called it a halo. And there was a bit of an argument about whether this was the way all of reality was set up, or whether reality was set up in this sort of band where you saw most of the stars. Well, it turns out that kind of people were both right and wrong about both of them, because this is really what we live in. This is the structure of stars and globular clusters. If you look at it face on, and now realize that you can't do this in real life, our galaxy is so gigantic that even if you spent your entire life trying to get away from it, you would never be able to see it face on the way we're showing it right now. But we can use data and information to come up with what this image looks like. And here's what we see. We see that there are arms of stars in a sort of spiral pattern in our galaxy. And we've named these arms of the stars after different constellations that those arms are concentrated in. So we happen to live in the arm called the Orion Spur, which is a small arm that's between two bigger arms, the Carina arm and the Perseus arm. And there are other arms that we can see as well. In the very center of our galaxy is a bulge of stars that are very different from the stars near us. The stars near us are of all sorts of colors, and we think that they were formed at different times, but the stars at the center of our galaxy are all relatively old, which means that all the blue stars have already blown up, died, and we're left with the red stars in the bulge of our galaxy. In the very center of the galaxy is something called a bar, sort of an elongated shape of stars, gives our galaxy a particular shape that we'll see other examples of as well. If we then look at the globular clusters, we find that they're kind of distributed around our galaxy. And in the right, you can see, looking at our galaxy edge on, in a kind of halo surrounding them. But most of the stars are either in that bulge at the center or in the disk. There are two different disks. There's a thin layer disk where there's a lot of dust, and then there's a thick layer disk where there's less dust and more stars. These are two different kinds of disks that we've observed, and they seem to have different characteristics. The thin disk has younger stars, the thick disk has older stars, but not quite as old as the bulge. You can also get a sense for the size and scale of our galaxy. The thickness of the disks are between 400 light years for the thin disk and 2,000 light years for the thick disk, where the distance from us to that central point of our galaxy is 26,000 light years. It would take like 26,000 years to reach that central point, an amazing distance. So we live in a barred spiral galaxy. And when we look out into space, we see different kinds of galaxies, and we see a lot of spiral galaxies. And I wanted to give you a sense for what the two different kinds of spiral galaxies are. One looks very much like there's a bar in the center, and the other one looks more or less like it's round, or sort of an unbarred spiral. Those are two different kinds of galaxies, and we believe that that's formed by gravitational instabilities as these galaxies are rotating around. Spiral galaxies have the unique feature that they rotate. There's another kind of galaxy which doesn't rotate. So we're now privileged to be able to really see our entire galaxy because we've had telescopes that could monitor the entire sky and stitch it all together. This is a telescope that was looking at our galaxy in the infrared, and that allows us to see through those dark, thick dust lanes that were obscuring our view. And when you put that all together, you can really see that we're in the center of a edge-on spiral galaxy, just like you see here. You can see that the disk has kind of a warp in it, which is sort of interesting. You can definitely see the bulge here. You can see how the distribution of stars changes between the thin disk and the thick disk and the bulge. Absolutely gorgeous and stunning way of looking at our galaxy using infrared light. And we need to use infrared light to be able to penetrate through some of those darker clouds that get in the way. So here's the map that we might have for our galaxy. We've got two kinds of disks, thin disk and thick disk, a bulge, something at the center, and then this halo where we were finding lots of these globular clusters that Hallow Shapley was looking at. We're going to find that the halo holds some other interesting mysteries as well. Here's another nice map of our galaxy with a few more of the arms indicated. Sometimes people see this picture and they think that it's a real picture, like someone took a photograph of our Milky Way. I want to emphasize that that's not possible. This is an artist's conception for the most part, based on lots of data. And it's a pretty good approximation of probably what it looks like. But to be quite honest, we can't go look at it. It's just too far away to get this view. Zooming in on one part of it, you can see the different arms and spurs where we're located and where some of the main features of the areas around us are, including some of these objects you've already been investigating in this class. Now, one of the interesting things about our galaxy, and indeed about all spiral galaxies, is that they rotate. And we can measure the rotation of galaxies in a lot of different ways, but perhaps one of the easiest ways to do it is to look at galaxies that are edge-on. And then if it's rotating, one part of the galaxy will be moving towards us and one part will be moving away from us. And we can measure that motion using the Doppler effect, just as we were using to discover things about exoplanets and discover things about binary stars. We can use it to discover things about galaxies. Now, when you play this game and you look and see how quickly a galaxy is moving towards and away from us at different distances away from the center, you come up with a really interesting plot. And that's what you see in red here, that it speeds up to a speed and then more or less stays constant, flat, all the way out to very high distances. The distances indicated here are in bizarre units called kiloparsecs. A parsec is about 3 light years. It's a unit of measurement that we come up with through using the parallax method. You can read more about that in your textbook, but you can just multiply this number by 3 to get a sense for thousands of light years. So if you see the number 10, it's really going to be 30,000 light years away. So you can see that this is going out to hundreds of thousands of light years. And when we observe the stars that are moving in rotational motion around the center of the galaxy, we find that they're moving sort of at a constant speed all the way out. This is a little weird because if you recall, the distribution of stars is really concentrated towards the center, not unlike our own solar system, for example. Perhaps not quite as concentrated as our solar system, but a similar sort of thing where most of the material's in the center and then there's less and less as you go out. And this seems reasonable when you first look at things, but if that were the case, you wouldn't expect a flat rotation curve. Our own solar system, we find that as you get further away from the sun, things slow down. That's under the influence of gravity and having all of the mass distributed right at the center. As you get further away, you're out at higher gravitational potential energies. That means you have lower kinetic energies and you move slower. But that's not happening here. We see that gravity is doing something bizarre, or there is some other material that has to be there that allows things to keep moving quickly. That blue line you see here is the expectation that astronomers had. They thought that the speeds would drop off as you get further away. But what we see in galaxy after galaxy after galaxy is that they are flat. This is one of the prime pieces of evidence for something called dark matter, some material that is dominating in galaxies, causing them to move in these bizarre ways, using the material itself as an extra oomph to get that speed up, using the gravitational motion, the gravitational force that increases that motion that allows it to speed at those speeds in the regular orbit. Now, this seemed bizarre and outrageous when it was first presented in the 1970s by a now famous astronomer, Vera Rubin. However, that seems to be the case. It seems like we have quite a bit of dark matter in our universe, causing galaxies to spin really quickly and causing some other interesting effects too that we will get to later as we talk about more things. Now, what if we look at the center of our galaxy? There are some really amazing things happening there. This is an image of the center of our galaxy using a radio telescope. And while the center of our galaxy just looks like a collection of stars, if you use optical or infrared, using a radio telescope, we can tell that there were lots of explosions and bizarre things happening. And there's a really bright spot right at the center we call Sagittarius A star. And this was a big mystery for a time. What could be causing all of this radio emission coming from the center of our galaxy? One suggestion was made that there might be a gigantic black hole at the center. And as material comes into the center and spirals into the black hole, it preferentially produces a lot of energy, perhaps in strange exotic wavelengths like radio or X-rays. And that's indeed what we think is going on at this point. This is what you see when you look at the galactic center in X-rays. And in the same sense that the radio is very bright, it's also very bright in X-rays. We don't have X-ray eyes, so we can't see this. But if we did, we would definitely notice something weird happening at the center of our galaxy. This is a close-up view using radio telescopes of what's going on at the center of our galaxy at Sagittarius A star. And it seems like there's just a lot of material that's being heated up to a great level, possibly spinning into this giant black hole. Now, this was just a conjecture for a while, but over the course of about 20 years, astronomers have been monitoring stars at the center of our galaxy, and they can actually see them move on orbits. And so what you see here, whenever you see a white dot, that's a star that has moved over the course of 20 years at the center of our galaxy, some 26,000 light years away. Since we know how far away the center of our galaxy is, and we know what time it takes for these paths to travel, we can connect the dots and figure out that there are these orbital motions that are happening at the center. You can really tell where that center of our galaxy exactly is, and there's nothing there. There's no star. But in order for this motion to happen, you can measure how big of an object it has to be to get these incredibly fast orbits. And you find that it has to be an object that has millions of times more mass than our sun. In order to concentrate that much material in that small amount of space and not have any light at all, we know that this has to be a black hole. So this was the observation which proved that there is a supermassive black hole at the center of our galaxy. And since we see similar sorts of things at other galaxies, we now have a pretty good understanding that essentially every galaxy in the universe has a supermassive black hole at its center. We're still not exactly clear how those supermassive black holes form. There were some hints in the last lecture that you might have come across, but that's what they are. They're there, and we need to admit that and understand it if we're going to really appreciate what's going on in our universe. Now, some students have the misconception that everything is orbiting around the supermassive black hole in the whole galaxy. And that's not exactly fair. Our galaxy has 100 billion stars. And while 1,000,000 times the mass of our sun is very massive, it's a tiny drop in the bucket compared to the mass of the entire galaxy. So when we describe the motion in the galaxy, although it is around the central supermassive black hole, the central supermassive black hole is not the thing that is causing that motion. The gravity of the entire galaxy is what's supporting the motion that we're experiencing around the center, a rotation that takes a few 100 million years. This is a way to look at what those orbits through our galaxy look like. In our situation, we're moving more or less in a plane. We find ourselves pretty close to the thin disk. And so we're sort of zipping around in that orientation. But if you move away from that part of the galaxy, perhaps out into the halo, the orientation of the orbits look a lot more random. And we'll see other galaxies that are organized in similar fashions. The Andromeda galaxy, which is the galaxy closest to us, is organized similar to our own. It has a plane of material and there's a rotation supported by dark matter. And you can see the distribution looks very similar to our own. We see the blue stars in the outskirts, the red stars near the bulge. Still, those dust lanes are showing up. This galaxy is actually moving towards us. We're in a gravitational dance with the Andromeda galaxy. In some billions of years, the two galaxies will merge. Now, the distances between stars are such that even when these two galaxies merge, individual stars won't collide. They'll pass right through each other. But it will make for some dramatic nights because we will see two galaxies instead of one in the sky. There's other galaxies that are closer than the Andromeda galaxy. They're just smaller. Perhaps the closest galaxy to us is one called the Sagittarius Dwarf, which is actually being actively destroyed by the galaxy that we live in, the Milky Way. The way galaxies get destroyed is through tidal actions. Tides tend to sort of stretch things out, and that's exactly what's happening here. Now, the individual stars are fine, but the arrangement of those stars in a coherent object gets completely disrupted as two galaxies interact. And when it's a big galaxy interacting with a small galaxy, we sometimes use the idea that the big galaxy is eating the small galaxy. And this might be what is going on with our Sagittarius Dwarf. Here you can see kind of how galaxies get disrupted when they're small and interacting with big galaxies. These big streams of stars start to get pulled off in both directions from the galaxy. We call those things tidal streams. And they persist sometimes for millions or even billions of years in the action of these smaller galaxies getting consumed by the large galaxy. Remember, I said that the Andromeda galaxy is going to collide with our own? Well, here is an artist's conception of what that will look like over the course of some 3 to 4 billion years. At first, the Andromeda galaxy is just going to become more dominant in our night sky, but then eventually there's going to be some interaction, some activity that happens. And we may end up with a very different galaxy at the end, sometimes called Milkomeda, which will not look like a disk galaxy anymore. It's going to look a little bit more roundish, maybe elliptical, maybe like a bulge completely with no disk. Now, there are some other nearby galaxies as well. There are two shown here on the left, the large and the small Magellanic Clouds. Those are the smallest or the nearest galaxies to our own Milky Way, which are coherent and easy to make out. In fact, you can see these with the naked eye if you go to the southern hemisphere. They're not visible in the northern hemisphere. Now, if we look out into the sky and we look at other galaxies, perhaps we look out in a place where we see a high concentration of them. One example might be in the direction of constellation Virgo, where we see lots and lots of galaxies. And in this image, anything that you see that looks kind of like a smudge in yellow is a galaxy. There's probably some hundreds of galaxies in this image. And at the very center of this image is something called M87. It's the giant central galaxy of this cluster of galaxies we call the Virgo cluster. One interesting thing about this giant galaxy, which is called a giant elliptical galaxy, is it's a very different form. We call it a morphology, a different morphology than our own Milky Way. And it, instead of having a disk and having star formation, blue stars, and then a bulge with red stars, it actually is kind of like a giant bulge. It has many more stars than our Milky Way, maybe up to 1 trillion of them. But there is no disk, and the orbits are all very random and much more like the orbits we found in the halo of our own Milky Way. So it's a very different kind of galaxy. Maybe up to 30% of galaxies we see are these giant elliptical galaxies, or sometimes there's also dwarf elliptical galaxies. So elliptical galaxies are one kind of galaxy, spiral galaxies are the other, and those make up the big two. There's also a kind of galaxy which doesn't really have a classification. We call those irregular galaxies. So when we look at the galaxies that are near our own, it's a little bit difficult because a lot of them are very small and hard to see. But this is approximately what we find. The Milky Way has some smaller satellite galaxies going around it. Andromeda has some smaller satellite galaxies going around them. And there's another sort of small spiral galaxy called M33 that is fairly nearby Andromeda. That makes up most of what we call the local group of galaxies. They're gravitationally bound together. Eventually, all these galaxies will merge, probably into something like a giant elliptical galaxy. But we can look out and see other varieties of galaxies as well. This one's called the Fireworks Galaxy. It's an obvious spiral galaxy. And we can see in those blue areas and some of the red bright spots that there are stars actively being born out of the disk of this galaxy. Here's another way to kind of think about spiral galaxies. Remember, we said that the Milky Way has various parts. Well, that's something we see in spiral galaxies. Spiral galaxies tend to have bulges and disks and spiral arms. If you see them edge on, they look very much the way we see in B. Here's a barred spiral galaxy. Remember, our own Milky Way is a barred spiral. Now, how do we make sense of all these different kinds of galaxies? Well, the first person to try to do something was Edwin Hubble, who came up with this diagram to try to arrange galaxies in different shapes and characteristics. He had the spiral galaxies, the barred and the regular spiral galaxies over on the right, and the ellipticals on the left. Now, Hubble thought that maybe there was some sort of progression happening where ellipticals turned into spirals. Now, we now know that ellipticals tend to be the result of lots of galactic mergers, whereas spirals tend to be the results of interactions that happen where there's a perturbation. There's a smaller galaxy that gets eaten by a larger group of stars and galaxies, and that's what causes the spiral shape. So it's not exactly the way Hubble thought of it, but we still use this organizational scheme because it helps us decide what kinds of galaxies we're looking at. Here we see some elliptical galaxies, right? These look very much more chaotic. There's lots of interesting things going on in terms of the orbits, but they're all sort of older red and dead stars. No dust to speak of, no star formation. How do we know how far away galaxies are? Well, one way we can figure it out is by looking for extremely bright supernovae. Supernova are the explosions of stars, and one particular kind of supernova, the type 1A, is the explosion of a white dwarf star, always happening at exactly the same size of the white dwarf, and therefore always giving off more or less the same amount of light. When we observe one of these supernovas in a distant galaxy, that light will outshine the light of the entire galaxy for a time. And if we can measure how bright that supernova is, that gives us a direct measurement for how far away the galaxy is. So supernova type 1A are going to be very important in our exploration of how far away galaxies are. As we began to measure how far away galaxies were, we saw that there was a relationship between the motion of the galaxy measured through their Doppler shift and how far away they were, except for those few galaxies that are right near us in the local group. As you move further and further away, we find that the galaxies are moving faster and faster away from us in all directions. And this seems to be a general feature of our universe. If you imagine ants standing on a ruler and that ruler getting stretched out, the ants would imagine that all the ants around them were moving further and further away from them. That's pretty much what's happening in our universe, except for the local group of galaxies. All the galaxies that are further away are moving away from us. And the further away the galaxy is, the further and faster it is moving. We call that the expansion of the universe. This is sometimes hard to wrap your head around, because we often think of expanding things as expanding into something. That's not really what's happening in our universe. Our universe is really just growing. It's not really growing into anything as far as we can tell. It's just that there's more and more space. And the further away something is, the more space that grows between those two things. Now, this might seem outrageous. We don't see that sort of thing happening in our day-to-day life. But it turns out that there are calculations that can be done using Einstein's theory of general relativity, which more or less predict that this could be a thing. And when we observe it to be a thing in our galaxy and in our universe, we come to understand that really we live in this expanding universe. Our own galaxy isn't expanding. When you're under the influence of local gravitational fields, there is no more of this expansion that's happening. It's only when things get far enough away so that there isn't a gravitational pull from one object to another, we call that a peculiar velocity, that you end up seeing this general trend of everything expanding away from everything else. Here's another way of thinking about it. This is called the raisin bread model. Imagine being a single raisin inside of a loaf of bread. And as the bread rises in the oven, all of the raisins get farther and farther away from you. Now, the problem with this analogy is that obviously the raisin bread is expanding into the pan in the oven. What you have to imagine is, as our universe, there isn't any outside. We're just inside of a raisin bread that's expanding, and it's not expanding into any. When we look really, really far out into the universe, very dim objects, in order to see those, we need to have excellent telescopes that can collect light for a long period of time. We see that every direction is absolutely filled with galaxies. This is one direction that we chose to point the Hubble Space Telescope based on the fact that we didn't see any really bright lights in that direction, no bright stars and no bright galaxies. But after many, many hours of integrating all that light, an enormous selection of galaxies, including lots of clusters of galaxies, show up. What are some other things that galaxies can do? Well, at the center of galaxies, we have these supermassive black holes. And our own central supermassive black hole isn't particularly active, although there's evidence in the past that material may have fallen in and caused a lot of fireworks and incredible explosions of energy. But there are other galaxies we look at where the central supermassive black hole is producing a lot of energy as things spiral down and heat up and shoot out away from the black hole. Remember, black holes themselves are not shining, but the material around them can. And that's what we see in this image here. This is M87, that central galaxy in the Virgo cluster. And we can see that there's a stream of material coming out from the center. It's called a jet. We can measure the speed of that material coming out, and it's very, very close to the speed of light. The only process we know that can accelerate material up to those speeds at that incredible amount is something like a supermassive black hole. And so these jets that form at the center of galaxies, where there's a lot of material coming in, these are indications of supermassive black holes all across the universe. Here's another indication of a supermassive black hole. This is a galaxy called Centaurus A, and it has these incredible radio lobes coming out of it. Remember that our own supermassive black hole produces a lot of radio light. Well, when there's an incredible jet that is expelled from the central supermassive black hole, that jet can also produce such an enormous amount of radio light that it can dwarf the amount of radio light produced by the rest of the galaxy, as is the case with Centaurus A. We've also been able to, at this point, use very clever radio technology called interferometry to get some of the first looks ever at the innermost part of the supermassive black hole disk. As the material is spiraling in, there is an empty spot in the center. That's exactly where the black hole lies. And that is what we would call the event horizon, the place from which no light can exit. Now, galaxies, of course, are interacting with each other. And as we said, Andromeda and the Milky Way will one day collide. We know what's going to happen in those circumstances because we can see different collisions that happen. So this is the collision of two galaxies called the antennae galaxy. You can really see some interesting things happening here as these two galaxies are colliding. Lots of really incredible things are happening. New stars are being formed, and the galaxies are combining into one. Here are some views of different collisions of different kinds of galaxies. I think this sometimes excites people more than anything else because this is some of the most beautiful imagery we have in the sky. Think about how long it takes for these interactions to happen. The timescales we'd be dealing with here would be hundreds of millions, if not billions of years. We notice that galaxies tend to come in clusters. And I already pointed out one cluster of galaxies, the Virgo cluster. Here's another cluster that's nearby called the Coma cluster. Every blue spot you see on here that's sort of azure in color is another galaxy in that Coma cluster. Here is yet another cluster of galaxies. This one's called About 2744. So many galaxies all clustered together. And one thing that we can see when we look at very distant galaxies like Abell 2744 is that the light from galaxies behind that cluster gets distorted, kind of in arcs. You can barely make it out in this image here, but those arcs are called gravitational lenses. It's the literal material of the galaxy cluster that bends the light as it travels through the universe. And we can use that fact to measure the mass of clusters. What's interesting is when we do this, we find that galaxy clusters are actually full of a lot more material than we even see here. Every single galaxy in this image has hundreds of billions of stars. But if you add all of them up, you don't get nearly as much mass as we can tell from when we measure the gravitational lens. This indicates that something like 90% of the mass in galaxy clusters is dark matter. Surprising amount. Something that remains something of a mystery, although we have some hints for what dark matter might be from the next topic we'll talk about, which is cosmology. This is a better view of what a gravitational lens looks like from behind a galaxy cluster. You can see that big arc, and measuring the precise shape of that arc actually tells you approximately what the mass of that galaxy cluster is. Here's another beautiful image of a galaxy cluster, and the gravitational lens arcs are unmistakable. As we move ever outward, we've been able to map many, many millions of galaxies, and we find that they make gigantic structures all across the known universe. This is one of the better maps that we have of this. This is moving out in distance. And one way we measure distance as we go further and further away is by using the redshift of the galaxies. Because all the galaxies are moving away from us, as they get further and further away, they're redshifted more and more. And so we can use redshift as a proxy for distance. The furthest distance we see in this image here is billions of light years. And so that's really, really far away, but we can still see lots and lots of structures. Many of these are much bigger than a cluster. We call them superclusters. And they form bizarre shapes. Sometimes they're stringy like filaments. Sometimes they're sort of large planes like walls. And there are enormous voids where there aren't hardly any galaxies out in our universe. An amazing thing to behold. We've been able to model how this can form using our understanding of dark matter and galaxies in general, and running a simulation of the entire universe. This is one of the examples of this run on supercomputers. And we mimic the same distribution of galaxies in these simulations as we see in real life. So we're coming to some understanding of how all of these galaxies formed, but there's still a lot of mystery left. We're going to spend some time in the next lecture really talking about the largest scales of the universe, trying to wrap our heads around this subject of cosmology and how it all comes together into one big reality. So So thank you very much for joining us. I hope that was an interesting and educational jaunt through galaxies. We have one more discussion left for the class where we'll talk about the universe as a whole, cosmology.